Okay, so we talked about, sorry, I got to get to Charles' Law. We talked about, I guess we could review Boyle's Law, which relates pressure and volume. And now we're going to go on to Charles' Law. Charles' Law is looking at temperature and volume. So if we take a balloon and we put it like in a freezer or put it in ice water, it's going to get smaller. So as we decrease the temperature, we decrease the volume. And so that would be that they are, as the temperature of an enclosed gas increases, the volume also increases. So they are directly proportional. And that's only if you keep the pressure constant. And so it says that the volume of a fixed mass or number of particles, or usually we talk about moles of a gas, are held constant. The gas volume is proportional to the temperature. So if we were to graph that, it would look like this. This is a direct relationship. As temperature is increasing on the x-axis, the volume is increasing on the y-axis. So that's basically how a hot air balloon works. We increase the temperature, we're holding the volume constant because the balloon is fully inflated and can't inflate anymore. And so the balloon will get bigger, or get the volume will increase. So as a hot air balloon, according to Charles' Law, as the temperature of the air increases, the volume of the balloon will increase. It will get to an exact maximum, though. So a balloon inflated at room temperature at 24 Celsius has a volume of 4.00 liters. If the balloon is then heated to a temperature of 58 Celsius, what is the new volume if the pressure remains constant? So our knowns we have 3 of, and the fourth one we're going to solve for. And we're going to use the equation V1 over T1 equals V2 over T2. And our unknown is going to be volume 2. And so when we we have to, in gas laws, always use Kelvin. We cannot use Celsius because Celsius has a negative value for temperature, and we can't have negative volume or negative pressure. So we have to use the absolute temperature scale, or Kelvin. So would we rearrange our equation to say V2 equals V1 times T2 over V1? You'll notice that T1 and T2 are inverted. And so solving for it, it'll increase to 4.46 liters. Remember, you will be having a quiz over this, so you do need to write this down, take notes, follow along, unless you're exempt, and then you don't have to. So, does the result make sense? The volume increased, the temperature increased, so yes, it does make sense. If you get something there, it decreased and the temperature increased, then you've probably inverted the two temperatures. So, here's your chance to show me what you know. So, the temperature of a balloon, what is the temperature of a balloon? 2.3 liters if it shrinks in volume to 0.632 liters when it's dipped in liquid nitrogen at a temperature of 77 Kelvin. So they want to know the original temperature. Go ahead and try and figure this out. Pause the video. So T1 is what we're solving for because that's the original temperature, equals V1 times T2 over V2. Everything's in Kelvin, and we get 276. And you are free to report in Kelvin if you wish. I will accept either Kelvin or Celsius unless I ask you specifically for one or the other. So let's go ahead and do Gay-Lussac's law. How are the pressure and temperature of a gas related? And if the temperature of a gas is increased and the volume is constant, then the pressure will also increase because now those particles are moving faster. They're hitting the walls of the container harder, which is how we measure pressures. How hard do they hit the side of the container? And so they are directly proportional. And this looks like it's inversely proportional, but if a number divided by a number is always equal to a constant, then that means they are directly proportional. And so that's this relationship. So P1 over T1 equals P2 over T2. And so this is how a pressure cooker works. We use a pressure cooker to reduce the amount of time that we're going to cook something, because we increase the pressure, the volume's constant, and by increasing the temperature, we increase the pressure, which will cause it to cook faster. And reversely, the reverse is also true. If you were to take something and go up to the top of Mount Everest, which is a very high peak, the pressure there, air pressure, is much, much lower than at sea level around here. And so if you were to try and cook something, you're going to have a harder time because the pressure is so much lower. Things will boil at a lower temperature, but they won't really cook. So that's why on a package like a box of cake mix always has the high altitude cooking directions. So aerosol cans carry labels warning not to incinerate or burn them or store them above a certain temperature, and that's because it will actually cause the can to burst, and when it ruptures, it's very violent and can be very dangerous. The gas used in the can is at a pressure of about 103 kilopascals, which is about 1 atmosphere, and at 25 Celsius. If the can is thrown into a fire, what will happen when the can reaches a temperature of 928 Celsius? And again, we have to convert first these temperatures to Kelvin, and we can leave kilopascals as kilopascals. It doesn't matter what unit you use other than temperatures. The only one you have to use Kelvin for. So we've got P1, T1, and T2, so we're solving for P2. And our rearranged equation, we add the 273, and we get P1 over T1 equals P2 over T2, and we are solving for P2. So P2 equals P1 times T2 divided by T1. Notice again, this is inverted, the temperatures. And when we substitute everything in, we get that the pressure will now be, that's weird. They have a weird way of doing that. 415 kilopascals, which is about, 4 atmospheres of pressure. That's pretty high. And from kinetic molecular theory, you would expect the increase in temperature of a gas to produce a increase in pressure if the volume remains the same. And that's because those particles are hitting the walls of the container at a faster velocity. And the calculated value does show an increase, so this is a good answer. Even if we don't calculate it correct, at least it did go up. So, pressure cooker containing kale. Why does it have to have kale? Kale's gross. And some water starts at 298 and 101 kilopascals. It's heated and the pressure increases to 136 kilopascals. What is the final temperature inside the cooker? So we are looking for T2. We have P1 and V1. P1 and P2, and we have T1. And it's already in Kelvin, so we don't have to convert it. And we would get T2 equals P2 T1 over P1. And we get a temperature higher than 298, which sounds about right, and it's actually at 400 Kelvin. So I'm going to stop here at the combined gas laws. I'll start there tomorrow. Thank you for listening. You have a great day.